Good afternoon, ma'am. For this presentation, our group will tackle Module 8, which focuses on momentum, impulse, and collisions. Since we did not make it in the face-to-face reporting, we decided to just make a simple PowerPoint together with our report and compiled it. And now, we will finally begin our report. Thank you. So the first subtopic under Module 8 is momentum of a particle. To begin with momentum, let us first give the definition of momentum, and not just momentum, but momentum of a particle specifically. The momentum of a particle is defined as the product of its mass times its velocity. It is a vector quantity. The momentum of a system is the vector sum of the momenta of the objects which make up the system. If the system is an isolated system, then the momentum of the system is a constant of the motion and subject to the principle of conservation of momentum, which we will tackle later on. Greater the mass, which is represented by m, and the speed of a particle, which in this case, if we're talking about momentum, is represented by v, which is its velocity. Then the greater is its magnitude of momentum, which is mv. So momentum is p is equals to mv, and p represents momentum. Keep in mind, however, momentum is a vector quantity with the same direction as the particle's velocity. The units of the magnitude of momentum are units of mass times speed, and the SI units of momentum are kilogram times meters per second. We often express the momentum of particle in terms of its components. If the particle has velocity components Vx, Vy, and Vz, then its momentum components Px, Py, and Pz, which we also call the x momentum, y momentum, and z momentum, are given by Px equals mvx, Py is equals to mvy, and Pz is equals to mvz. Next, we will be moving on to some sample problems. And now for the sample problems. We have two sample problems here, and we will go with the first one. So it says here, if a truck has a mass of 1,000 kilograms and is traveling with a speed of 50 meters per second, then what is its momentum? So first step in solving an equation is to write the given first. So we have 1,000 kilograms, which is the mass, and 50 meters per second, which is the velocity. And we will find momentum, which is p. Now we know that the formula for momentum is p equals to mv, which is momentum equals mass times velocity. Now this is a simple one because the mass and velocity is already given in the problem. So for the solution, p equals mv, substitute mass for 1000 and 50 meters per second for the velocity. So P, or momentum, is equals to 1000 kilograms times 50 meters per second. Then our momentum will be 50,000 kilogram meters per second. Kilogram meters per second being the unit for momentum. And for the second one, an 8 kilogram bowling ball is rolling in a straight line towards you. If its momentum is 16 kilogram meters per second, how fast is it traveling? So first step is to write the given again. So we have here our mass, which is 8 kilograms, and we have here our momentum, which is 16 kilogram meters per second. In this case, we will find velocity. So even though we're talking about momentum here, we can also derive velocity from the formula of momentum, which is P equals mv. So to derive velocity using that formula or equation, see that P is equals to mv, then we just need to divide both sides by m to equate velocity. So in that case, we will be able to solve for its velocity. So if we divide both sides by m, which is mass, then velocity is equals to p over m, or in other terms, velocity is equals to the momentum divided by the mass. So let's try to solve it. So for the solution, velocity equals p over m. Then we have the mass and the momentum given in the equation. Then all that's left to do is to substitute the given. So velocity is equals to p, momentum, which is 16 kilogram meters per second, over mass, which is 8 kilograms. So we divide 16 by 8, so that will be 2. And then we will cancel kilograms, and what we're left with is meters per second. So our answer will be 2 meters per second, and that is correct because we're, we're finding the velocity, and the unit for velocity is 2 meters per second. So that's how you can derive um, velocity using the formula or equation for momentum. Thank you.
Good day, everyone. I am Pauline Ambal, and I am here to discuss impulse and momentum. A particle's momentum and its kinetic energy both depend on the mass and velocity of the particle. To see the physical difference between momentum and kinetic energy, we must first define a quantity closely related to momentum called impulse. Impulse is a vector quantity, and its direction is the same as the net force. Its magnitude is the product of the magnitude of the net force and the length of time that the net force acts. Moreover, impulse is the change of momentum of an object when the object is acted upon force for an interval amount of time. The equivalence between momentum and impulse is known as the impulse momentum theorem. So, what is the impulse momentum theorem? The impulse momentum theory states that the impulse applied to an object is equal to the change in its momentum. It shows that the change in momentum of an object depends not only on the amount of force applied, but also on how long the force is applied. The impulse momentum theory is used to describe the relationship between the change in momentum, average net force, and time interval. The change in momentum of a particle during a time interval equals the impulse of the net force that acts on the particle during that interval. This is important in analyzing what happens during collisions and impact sports. Next, for our example, we will answer this problem. You throw a ball with a mass of 0.40 kilograms against a brick of wall. It hits the wall moving horizontally to the left at 30 meters per second and rebounds horizontally to the right at 20 meters per second. Find the impulse of the net force on the ball during its collision with the wall. For our given, we have the mass at 0.40 kilograms and initial velocity at negative 30 meters per second because it was moving horizontally to the left. Next, for our final velocity, we have 20 meters per second because it is horizontally moving to the right. With our choice of x-axis, we will then find the initial and final x components of the momentum of the ball. For P1, we will multiply the mass times v1, which is negative 30 meters per second. This will result in negative 12 kilograms times meters per second. For P2, we will multiply the mass again times the final velocity, which is 20 meters per second, and this results to 8 kilograms meters per second. And then we will compute for the impulse through the impulse momentum theorem, which is J equals P2x minus P1x. And then we will just substitute all the components, and then it will result into 20 newtons times seconds.
Hello, I'm Ethan C. and I'll be discussing the conservation of momentum. Conservation of momentum is a fundamental principle in physics that states that the total momentum of an isolated system remains constant if no external forces act on it. In simpler terms, the combined momentum of interacting objects before a collision or explosion is equal to the combined momentum after the event. This principle plays a crucial role in understanding and analyzing various physical phenomena, including collisions, explosion, and other interactions between objects. The conservation of momentum is derived from Newton's laws of motion and serves as a valuable tool for predicting and explaining the outcomes of dynamic events in the physical world. Here are some equations that describe the conservation of momentum. The first one is the vector sum of momentum in the system. So the total momentum can be simply described by the sum of the vector momentums in the system. The second equation equates the momentum into its expanded form, which is just mass times the vector velocity. And taking the sum of it will give you the total momentum. If the external force of the system is zero, then the total momentum will stay constant. An example of this principle is, let's say two objects are colliding. If there are no external forces acted upon in the system, it does not matter what is the mass and velocity of the two objects before they crash and after they crash. The momentum before and after will stay the same. These are called collisions, and we have a plethora of equations and formulas that describe them. But we can only describe them due to our understanding of conservation of momentum. The formulas will be further explained later on the video.
Good day, I will be discussing elastic collisions. We saw in section 8.3 that an elastic collision is an isolated system in which kinetic energy as well as momentum is conserved. Elastic collisions occur when the forces between colliding objects are conservative. An example of this elastic collision is when two billiard balls collide. They squash a little near the surface of contact, but then they spring back. Some of the kinetic energy is stored temporarily as elastic potential energy, but at the end it is reconverted back to kinetic energy. So for the first formula, let's look at a one-dimensional elastic collision between two objects A and B, in which all the velocities lie along the same line. We call this line the x-axis. So each momentum and velocity has only an x component. We call the x velocities before the collision velocity A of 1x and velocity B of 1x, and those after the collision V of VA to x and VB to x from conservation of kinetic energy. So in the second formula, we can see here M stands for mass. Mass of the M of A is mass of the first object. M of B is the mass of the second object. So VA of 1x is the first velocity of the first object, and VB 1x is the first velocity of the second object. VA 2x is the final velocity of the first object, and VB 2x is the final velocity of the second object. So if the masses of M of A and M of B and the initial velocities, velocity A of 1x and VB1 of x are known, we can solve these two equations to find the final velocities VA to x and VB to x. We will use the second formula given here. Since the given, we could solve them using that equation. Now let us move on to elastic collisions, one object initially at rest. The general solution to the above equation is a little complicated, so we'll concentrate on a particular case in which object B is at rest before the collision. So this means that the velocity of the second object is 0. Think of P as a target for object A to hit. Then the kinetic energy and momentum conservation equations are respectively. So let's think of it this way. Let's say a ball is going to hit a stationary box. So the box is stationary, meaning our box is our second object, meaning its velocity is 0. So here we can see in the third picture that compared to the first and second pictures, we remove the first velocity of B of 1x, since, as I've said, since it is an object at rest, meaning 0, so 0 times anything other than it will result to 0. That's why here in the second object we remove it. So we can solve for VA2x and VB2x in terms of masses and the initial velocity A of 1x. This involves some fairly strenuous algebra, but in the end, after some solving and algebra, we get to this equation, which is the fourth equation. The velocity B2x is equals to 2 times the mass of A over mass of A plus mass of B times velocity of A. I will be discussing elastic collisions and relative velocity now. So here in the fifth formula, the one on top, here VB2x minus VA2x is the velocity of B relative to A after the collision. This equals to VA1 of x, which is the negative of the velocity B relative to A before the collision. The relative velocity has the same magnitude but opposite sign. Before and after the collision, the sign changes before A and B are approaching each other before the collision but moving apart after the collision. If you view this collision from a second coordinate system moving with constant velocity relative to the first, the velocities of the objects are different but the relative velocities are the same. Hence, our statement about relative velocities hold for any straight line elastic collision. Even with neither objects is at rest initially, in a straight line elastic collision of two objects, the relative velocities before and after the collision have the same magnitude but opposite sign. This means that if B moving from collision, it will result in this formula, the sixth one. The VB2x minus VA2x is equals to negative VB1x minus VA1x. So to get us a better understanding of this, let's say we have two balls. Two balls are in a straight line and they are going to impact against each other. So this ball going here, this ball going here, they will hit each other and they will eventually bounce back. Same magnitude but in opposite direction. So it turns out that a vector relationship similar to this is a general property of all elastic collisions. Even when both objects are moving initially and velocities do not lie along the same line, this result provides an alternative and equivalent definition of elastic collision. In an elastic collision, the relative velocity of the two objects has the same magnitude before and after the collision. Whenever this condition is satisfied, the total kinetic energy is also conserved. So that is all for elastic collision. Let us now proceed with the examples. Let us proceed with the example. A 5 kg ball moving east at a speed of 8 meters per second strikes a 3 kg ball at rest. Calculating the velocities of the two balls, assuming a perfectly elastic collision. So based on the problem, let us first get the known values so we can formulate our equation. The first mass is given as 5 kilograms. The velocity of the first object is 8 meters per second given in the statement. The mass of the object at rest is 3 kilograms. So since, as we have said, it is an object at rest, meaning its velocity is 0. That's why our V2 is 0. So as we can see here, there are two missing variables. Therefore, we need two equations to get those two missing. For any collision, be it elastic or inelastic, momentum is always conserved. This question is an elastic collision. Based on the problem, it says it is a perfectly elastic collision, meaning that the kinetic energy is also conserved. However, it is not conserved for an inelastic collision. So, since this is an elastic, it is conserved.
Hello again. So here is the example of collision and its solution. At letter A, it shows the equation of conservation of momentum. It shows the initial total momentum is equal to the final total momentum. And after substituting and equating, you'll get that 40 is equal to 5 final V1 plus 3 final V2. Now in letter B, it is the relative velocity equation. V1 plus final V1 is equal to V2 plus final V2. After substituting, you will get 8 is equal to final V2 minus final V1. At letter C, we are going to solve for our value already. And I chose to solve for V2. So in order to solve it, I will use a substitution method in this. And the first equation is derived from the equation at letter B, where final V1 is equal to final V2 minus 8. And substituting that into the equation we got at letter A, you get that the 5 times the quantity of final V2 minus 8 plus 3 times the final V2 is equal to 40. After equating it all, you will get that V2 is equal to 10. Now at letter D is a very simple. You just take the equation again and substitute what we solved at letter C. So final V1 is equal to 10 minus 8, and that is 2. So the final answer is the final V1 is equal to 2 meters per second, whereas the final V2 is 10 meters per second.
Okay, let us proceed with the example. A 5 kilogram ball moving east at a speed of 8 meters per second strikes a 3 kilogram ball at rest. Calculating the velocities of the two balls, assuming a perfectly elastic collision. So, based on the problem, let us first get the known values so we can formulate our equation. The first mass is given as 5 kilograms. The velocity of the first object is 8 meters per second given in the statement. The mass of the object at rest is 3 kilograms. So since, as we have said, it is an object at rest, meaning its velocity is 0. That's why our V2 is 0. So as we can see here, there are two missing variables. Therefore, we need two equations to get those two missing. For any collision, be it elastic or inelastic, momentum is always conserved. This question is an elastic collision. Based on the problem, it says it is a perfectly elastic collision, meaning that the kinetic energy is also conserved. However, it is not conserved for an inelastic collision. So, since this is an elastic, it is conserved.
What is a rocket propulsion? The energy employed by the rocket to lift off from the Earth's surface and descend into the atmosphere is derived from the application of Newton's third law of motion. In this process, the fuel is expelled from the nozzle, generating an equal and opposite reaction. A propulsion system is designed to generate thrust, propelling an object forward. In spacecraft, it is frequently necessary to use a propulsion system to rectify errors in launch vehicle injection and address orbital perturbations. The propulsion system typically consists of three components: an energy source, such as the fuel tank, a mechanism that converts the energy source into mechanical energy, the engine, and the final actuator that applies the thrust force, the crew propeller.
The force exerted by a fluid can be calculated by the force exerted by a fluid is equal to the mass free of the fluid over delta m and delta t, multiplied by the velocity of the fluid. We have to find the mass fluid in kilograms per second. Delta m equals to the change in mass is 750 kilograms, over delta t is equal to the change in time is 60 seconds or 1 minute. So 750 kilograms divided by 60 seconds is equals to 12.5 kilogram per second. The force exerted by a fluid is equals to 12.5 times negative 85 meters per second. So the force of the fluid is negative 1062.5 Newton. The answer is negative because the force is directed to the x-axis.